Hello everyone, welcome back. Today we are going to talk about the concepts of modeling. This is from the class of simulation and modeling. And so let's get started. So the first thing we are going to discuss is what's the definition of model. So as you can see here, we define a model as the body of information about a system gathered for the purpose of studying the system. So we are gathering some information about something, especially a system. We are gathering this information for studying the system. And the formal definition of system, what is system? A system is a group of interacting, interrelated or interdependent elements forming a complex whole. So something that is trying to solve a complex problem via interacting, interrelated and interdependent elements, that is a system. And for that system we are going to try to formulate some body of information. Each of those body of information can be specified or noted as models of the system. So now let's talk about why do we need modeling. So to study a system, sometimes possible to experiment with the system, however most of the time impossible to experiment with the system itself, meaning we are trying to uh, see new ideas or trying to implement new concepts while a real-time system is currently running, because the experiment might hamper workflow of the system. So for that we are trying to do models and experiment with the whole system separately in a simulated environment. And as an example, as you can see, you cannot modify supply and demand to study economic system. We have to build a model. So it's a very simple and understandable example. And here there are some points to remember. Since the purpose of the study will determine the nature of information that is gathered, there is no unique model of a system, meaning the model of a system that you are going to create may be different based on what you are trying to study of the system. The purpose of the study will determine the model. So that's a very important point to remember. Then different models of the same system may be produced by different analysts for different aspects of the system, meaning a different study might result into a different type of simulated system with different types of models on the same real world system. Okay, so a same analyst may change the whole model of a system that he or she is designing because of the underlying understanding may have changed. So that these 3 points are very important to remember regarding any kind of system modeling. So now let's talk about driving a model. um, okay, the task of driving a model, two subtasks, and they are establishing the model structure and then supplying the data. And establishing the model structure, to establish the structure, what we need to do is determines the system boundary. We need to determine the system boundary, and then we need to identify the entities, attributes and activities of the system. So these two steps will help us structure the models that we are going to create. And we have already read about this previously. And the data provides the values the attributes can have and define the relationships involved in the activities. They are defined as part of one task rather than two different tasks. So these values, the attributes and the activities are kind of one task, so they are not two different tasks, meaning this one is a single task, identifies the entities, attributes and activities of the system. These should not be subdivided into separate tasks. Let's see what are the entities, activities and attributes. For that we need to understand system boundary. System boundary is the line that separates the system with its environment. We have talked about this. So we must define the scope of a system before simulating any kind of system, because if you do not define the scope, the overall simulation might even get complex as we broaden the scope. So we need to specifically draw the boundary, the exact contextual area that we need to study, and then we will be able to understand the internal entities, attributes, and activities. What are the entity? Entities are objects of interest within a system. The thing we might be interested in, a specific machine maybe, or a specific entity, or a specific people, a group of people, a specific job, a specific task maybe. So these are entities. And then what are the attributes? Denotes a property of an entity. So the value or property is of an entity is attribute. A very simple definition. We already know that. And what is the activity? Any process that changes within a system is called activity, meaning something that may cause change, and that is an activity. So next we may go and see some examples. Say, let's say we're trying to simulate a system that handles traffic, and then the entities may be cars, attributes may be like speed and distance, and activities like driving. So this is a simple example, and from the same perspective, if we are trying to simulate a simple system of the bank, the entities may be customers, and attributes may be balance and credit status, and activities may be depositing. And as you can see, these are some more examples. So now let's try to think about the types of models. So basically, models are of two categories. Actually, we are actually seeing here two, but there is a third category. We have talked about it previously, the process model. However, here in this specific context, we are going to talk about only these two. However, do remember the model categories of model are three, and not only these two. It's the physical model, mathematical model, and process model. So what is these two specific models, the physical and mathematical, can be divided into two separate specific classifications, like the static or dynamic. So let's dig into these two types of models. The first one is physical model. Physical model is based on some analogy, similarity between such systems as mechanical and electrical, or electrical and hydraulic driven by fluids, meaning something that has some physical similarity with the system. We need to model those, then we are trying to model physical models. And system attributes are present, voltage of or position of a shaft, maybe a specific thing that you can see and differentiate from other entities of a system, and we may need it one-to-one mapping, and then we are going to use the physical model. Reflects the physical laws that drive the model. Yes, so that establishes the idea. Next one is the mathematical model. So mathematical model is some symbolic notation and mathematical equations to represent the system. So we are going to actually not physically one-to-one map. In this case, we are going to create equations that actually imitate the behavior of the different specific parts of a system, and for those things we are going to use mathematical model. System attributes are represented by variables or activities by mathematical functions. So in this case, the model is the equation, and the attributes are variables, and activities are functions. So now let's talk about another way of classifying models, as we have already discussed previously in these two slides before this, that is the static and dynamic models. Static models can only show the values that system attributes take when the system is in balance. And for dynamic models follow the change over time, not like sudden changes. So they follow change over time and the result from these system activities. We are actually familiar with this concept. So now let's see more about mathematical models. In case of mathematical models, there is another type of model, that is the solved model. And solved model is a third distinction, is the technique by which the model is solved. And a distinction can be made, and that is the analytical and numerical methods. Analytical uses the deductive reasoning of mathematics theory or mathematical theory to solve a model, and numerical methods involve applying computational procedure to solve equations. So these two ways of solving a model, if a specific mathematical model can be solved via either analytical way or numerical way, then those type of models are can be classified as solved models, because not all mathematical models are solvable, as they are random in most cases, just equatively representable but not directly solvable, because they depend on various kind of real world actions, or various kinds of environmental change or system changes from the system and all that. So let's look at the whole block of categorization. The system models are of two types here. The first one is physical and the second was mathematical. And then each of these two types can be divided into static model and dynamic model. However, mathematical model is also has a different type, that is called the solved model. And this solved model has two different types, that is the analytical model and numerical model. Next, let us talk about the principles used in modeling. It is not possible to provide rules by which mathematical models are built. So there are not specific or globally accepted rules, but these are some principles that you can follow. A number of principles can be stated to actually help us get some conceptualization of the models that you're going to build. The first one is the block building, should be organized in series of blocks. Then that is next one is the relevance, relevant to the study objective. Next, accuracy of information gathered from the system should be considered. Then the last one is the aggregation, aggregation in the extent to which the number of individual entities can be grouped together into a larger entity or large entity. So for this concept, we are going to understand a system a bit more differently. A system is a set of interacting objects, as you have discussed before, but description of a system can be made many levels of details. So we can define a system as much specifically as you want. However, as you can see, a system consisting of interacting subsystems, and again a subsystem consisting of subsystem, lower level of details. A system study must begin by deciding on the level of subsystems details to be used. However, we have to decide the level from the beginning, so that we do not make the whole system too much complex for the simulation or whole objective we are trying to achieve here. Now, let's take a deeper look into the principles used in modeling. So the first one is block building. Here, we are going to describe the system as a series of blocks. So the few or preferably one input, and that is also a block, results in few output variables, and the system interconnections between the blocks. As you can see, here is an image. Here there are 5 different blocks, and there are some inputs like the block here. The purchasing department has the raw materials as input, and also the production control department has customer orders as input. And there is also the fabrication department, the assembly department, the shifting department, and also the finished products. This is the output. So these 5 specific squares are the blocks of a specific system, here a factory system, and they are interconnected in various ways, and some of them have some inputs and some of them has some outputs. Like, as you can see, each of the following blocks under the production control department has kind of 2 inputs and 1 output. The production control department has 1 input and 4 outputs. So let's go to the next principle, the relevance principle. Here the model should only include relevant to study objective. So we should actually exclude all those models or all those concepts that are outside the objective of the study we're currently performing. And for example, if factory system study aim to compare effects of different operating rules or on efficiency, then it is not relevant to consider hiring of employees as activity. So your target is to understand the effects of different operating rules on efficiency. So you should not be considering hiring the steps to hire employees as an activity in this specific version of a simulation model. If you consider outside is models outside the scope of your objective, it may not do any harm to the system, but your system will become more complex. So let's go to the other two principles, that is the accuracy and aggregation. Accuracy is the accuracy of information for model should be considered. So when we are trying to simulate or create models, we are actually studying the existing system or a system that we are conceptualizing. So your ideas or conceptions or the study information should be accurate. So any kind of wrong information or inaccurate information may mislead your simulation in a different direction. So that's bad. So you need to consider about accuracy. Then the final one is the aggregation, in the extent to which the number of individual entities can be grouped together into a large entity. This means when we have divided or identified all the blocks of a system and we are actually sure of the relevance, that they are all relevant to our study and all the information are accurate. However, if we see that we have dug too much deep into the system, we divided all the components a bit too specifically, we can aggregate the specific connected components into a larger component, so the number of blocks become less, so the complexity becomes low, and the overall simulation time and the goal achievement time and all the process related becomes easier. So as you can see here, general management is satisfied with this description, but production manager may not be satisfied with this specific block building model, because production manager will need to know more details under each of these specific blocks. The purchasing department, what are the interdependent blocks under this department, the fabrication department, and all that. Now let us look at a real world scenario regarding the corporate model, where we are going to use the principles of modeling. And models of this nature are called corporate model. Different corporations use this model in various aspects of planning their operations. These are the three blocks at a very top level. There is the environment block, the management block, and the plant block. And each of these blocks are connected to each other by a single arrow, as you can see here. Major segments of a corporate model. So let's dig into the corporate model. What is it? Assume the corporate is a manufacturing industry. So we're assuming any kind of manufacturing industry. It's planning to produce and market some new products. At first level of detail, might consider the complete model as consisting of three parts. At first level, we are considering the whole model as consisting of three parts, each of a different general nature. A corporation operates within an environment. There is an environment, there is a market, there is target people, there is target products and all that, competition and all that. Then a physical plant, where the industry, where the production will happen. Means of production is the management system, policy making aspects, the handlers or the decision makers or the admin body. So these are the three aspects of a specific corporate model. So let's dig into each of these specific top models. Now, if we look deep into the subsystems of the environment segment here, as you can see, the major element is the market, the output is demand, and input is price and supply. So there are four blocks to consider here: the population and the competition. And population is actually getting some pushing the competition, and also the population is pushing the market, and competition is also pushing the market. The marketing is also affected by price and supply, and also the national economy. And all these actually gets our demand into the specific industrial concept. So this is the environment segment, and for the production segment, there are four blocks here too. The main input is the labor and machinery, and the output is supply. As you can see, the production block here is actually getting input from labor, machinery, and also from world economy and national economy. And production is getting output to distribution and supply. the production segment, and the management segment is here. Its main input is demand and investment, and also the main output is price to be set and profit to be achieved. Here, this one is a bit more complex. The main segment is actually the finance and the pricing. Finance is the financing is getting affected by investment, of course, and it is actually providing labor and machinery. It's also getting affected by world economy and national economy. And finally, pricing is getting affected by national economy and financing, and also forecasting, which is coming from demand, and pricing is also going outputting profit and price. Now if we look as a look at the whole system as a full corporate model, all the specific components and the subsystems are interconnected here. As you can see, the production segment here, the financing segment is also here, and the market is there. So each of these blocks are interconnected. The financing is getting input from investment, and it is providing labor and machinery for our production, and each of these two blocks are getting environmental input from national economy and world economy, and then production is getting their products ready and distributing it. It's supplying the into the market, and the market is getting input from population and also competition and also price. And according to the market, the demand is getting ready, and it is forecasting the number of products we should make, and it's also assigning our price, and then it's giving us some profit. So this is the whole corporate model. It's very simple, not complex. Just you need to understand each of these specific models or specific blocks separately, and they all come together here in this block. So now finally we'll be talking about some types of system study, and this is the final topic of this lecture. And for that, use of corporate model. Having developed a model, it could be used to study a system. So we're studying a system in three different ways, and they are system analysis, system design, and system postulation. Now system analysis refers to understand how an existing system or proposed system operates. In ideal situation, investigator will be there, able to do some experiment with the system, and if what actually done to construct a model of system and investigate the model. So a system analysis study of system study, we actually have an existing system, so we study that system and investigate some problems and generate ideas to solve those problems, and based on these ideas we will design our final system. And the next way of study is the system design. The objective here is to produce a system that meets some specification. Certain system parameters or components are chosen by designer, and conceptually he chooses a combination to construct the system. So here we are actually trying to design a separate kind of way to achieve the target of the system. We are utilizing the current components of the system, and in that way we're actually not changing the system in a too much drastical way. However, this way of studying is called system design, using the existing parameters or components. And the final one is system postulation. In this way of system study, we actually postulate or hypothesis or try to think about a totally new solution, and if we will be able to do some proper work using that concept. And it is the characteristic of the way models are employed in social, economic, and political and medical studies most of the time, because these are kind of not too much clear from the start, this kind of studies, social, economic, political, and medical studies. So where the behavior of the system is unknown, but the process that produces the behavior is known. So we actually conceptualize that if we follow these kind of steps, this will happen, and proceed with the concept. And that is the hypothesis, and as of the synonym is postulate, system postulation. So these are the three ways of system study. That's it for this lecture.